Most modern software applications are using REST APIs. But what is REST and what is REST API? Let's understand in this video. Before understanding REST API, let's quickly understand what an API is. API is a way for one application to request data or perform an action in another application. Consider it like a way of two applications communicating over the web. As web-based systems became more common, developers faced several challenges. No consistent API design, tight coupling between client and server, poor scalability, and more. So, Roy Fieldings introduced REST to solve these problems. REST stands for Representational State Transfer. REST is not a programming language, not a framework. It is an architectural style and is based on 6 architectural principles, also called as constraints. The client-server constraint states that the client and the server have separate responsibilities. For example, when you open Instagram, your phone sends a request, and Instagram server processes that request and returns the required data. The client focuses on displaying information while the server focuses on storing the data and handling the business logic. This separation allows client and server to evolve independently. Client can be upgraded or changed without informing the server, and the server can be upgraded or changed without informing the client. Client doesn't need to know about the business logic or programming language of the server, and the server doesn't need to know what technology is being used in the client. The uniform interface is the core architectural constraint of REST that dictates a standardized, consistent way for clients and servers to interact. It has following 4 aspects: identification of resources, manipulation of resources through representation, self-descriptive messages for each request, and HETEOS, hypermedia as the engine of application state. Let's see them one by one. Every piece of data exposed by the API is treated as a resource, and each resource should have unique URI that identifies it. Clients interact with resources using these URIs instead of accessing databases or internal implementation details directly. For example, /users /123 identifies specific user, while /orders /456 identifies a specific order. Clients do not modify resources directly. Instead, they send a representation of the resources, such as JSON or XML, to create or update it. The server processes representation and updates the actual resource. For example, a client sends a JSON object containing updated user details in a put request to modify a user. Each request and response should contain all the information needed to understand and process it. This includes the HTTP methods, headers, status codes, content type, and the message body. For example, a response with 200 OK, content type as application/JSON, and a JSON body clearly tells the client what the response contains and how to interpret it. A server response can include links to related actions or resources. This allows clients to discover what they can do next instead of hard coding every endpoint. For example, when fetching an order, the response may include links to view payment details, cancel the order, or track the shipment. The client shows these links to navigate the APIs dynamically. Combining all these 4 aspects of uniform interface principle, the key takeaway is REST API should communicate in a consistent way. Resources should have meaningful URLs, use standard HTTP methods, and follow standard formats for requests and responses such as JSON or XML, along with the standard HTTP status codes. Instead of inventing different ways to communicate for every API, REST encourages common and consistent conventions. This makes APIs much easier to understand and integrate. Every request should contain everything the server needs to process it. The server should not remember information from previous request. For example, if you want to update the details of customer 123, the request should contain everything required to process that update, such as the authentication details, customer ID, and the information to be updated. The server should not depend on information stored from previous request in a server-side session. If the server has to maintain this kind of state for every client, it consumes additional memory and makes scaling the application more difficult. With the stateless principle, each request can be processed independently. This makes applications easier to scale and more reliable. The cacheable constraint says that every response should indicate whether it can be cached or not. If a response is cacheable, it can be reused for the future request instead of requesting the same data from the server again. Some resources don't change very often. For example, your profile picture or a company logo may remain the same for a long time. Instead of downloading it every time, the client can reuse the cached version. This improves performance and reduces the unnecessary network traffic. In a layered system, a client doesn't need to know how many systems handles its requests. Each component only needs to communicate with the next layer without needing to know what lies beyond that layer. For example, a request might first go through an API gateway, then a load balancer, and then finally reach the application server. From the client's perspective, it simply sends a request to the API gateway. It doesn't need to know whether there is a load balancer or multiple application server or any other system behind it. This allows each layer to be changed or added or scaled independently without affecting the client. The final constraint is code on demand, and it's optional and less common. It says the server can send executable code to the client when needed. The server can send JavaScript or other executables. The client executes that JavaScript to provide interactive features or dynamic updates. These are the 6 constraints of REST. API that follows these 6 constraints are called as REST APIs. In practice, many APIs don't implement every REST constraints completely, yet they are still referred as REST APIs. In general, the closer an API follows REST constraints, the more RESTful it is. Over the years, developers have also adopted additional conventions such as API versioning, pagination, filtering, sorting, and standardized error response. While these are not part of the original REST architectural constraints, they have become common practices in modern REST API design. I will explain these conventions in another video. Thanks for watching. I'll see you in the next one.